All right. So, hi everyone. Welcome back to the Python course. And what we're going to be talking about today is kind of an extension about what we did in our previous lesson, where we looked at linear and logistic regression. Basically, we're going to be looking at some other machine learning and statistical models and explain why we might use them and the kinds of preparations we might need to do in order to use them. And that'll make a little more sense as we go forward. So I'm using the same data set that we have been using for a little while, DAC lesson. For anybody unfamiliar, that is basically a collection of data on Airbnb listings in the New York City area. So I'm getting my relevant columns, and I am filtering only to 1,000 random samples, and that was simply done to decrease the runtime of the models. You don't usually need to do that if you're working in a real data scenario, but for pedagogy to make sure everything runs smoothly and quickly, I've done this. So machine learning is basically a subfield of AI that refers to models that can learn from data and perform some action based on what they have learned. So there are really two easy ways to think about this, and those are supervised models and unsupervised models. A supervised model will look at existing data, learn from it, and then use that information to predict an outcome. So let's say with this Airbnb data, we're trying to predict the price of a listing based on a bunch of other information about it. We might have a data set that has all the information and the price in it, and we can tell a model to learn with that data how to predict the price. And now, once we have the model trained, we can look at another data set that has the information but not the price and predict the price for that new data using that trained model. So basically, you can use it to predict a numeric outcome or the category that something belongs to. And those are referred to by different names. And the first one we're going to look at is regression, which predicts a numeric outcome. I'm only using a very small subset of models that can be used for supervised learning. So be aware that there are plenty more options for you to choose from, and certain ones are going to be more relevant depending on your data. And you'll see what I mean by that here. This one here is a form of support vector machines that is designed for regression, hence its name, support vector regressor. It requires two things to be true. One, the predictors must be continuous. That is, the data that it learns from must be numeric, and they must have an infinite range. And then the predictors must be scaled. Basically, think of it like unit conversion in a way. Basically, what you're doing is looking at all of these different numeric predictors and saying, hey, I want to see how they fall on a scale from 0 to 1. And it'll do that for all of your predictors. And it has to be done that way. You have to scale your data for this model because the mathematics behind the model will get skewed if you don't scale your data. And if you really want to dig into that, you can look into the actual mathematics behind support vector machines, but we're not going to cover that today. So what I'm doing here is first defining what the, okay, we're first defining our outcome, that being our y variable, and then our x being everything that determines the y variable, right? And we're doing a simple 80-20 split for our training data and our validation data. Basically, we need to give it data for it to learn from and data to test its predictions with. And if that's a little confusing, I go more into depth of that in the previous video that I taught linear and logistic regression in. And here I'm just scaling the data, and you have to scale both your dependence training and your dependence validation data, because otherwise it's not going to be able to work with this validation data. And here, this is pretty standard syntax for any model that you use within the sklearn or scikit-learn package. And this package here includes a huge number of statistical or machine learning models, and they're very easy to implement, hence why we're using them here. So here I'm just defining that I want to use support vector regressor, and now I'm training the model by feeding it my training data, both the independence and the dependence. And then I'm generating my predictions and storing them into a list. All I'm doing here is seeing the difference between the predicted value and the actual value, and then calculating that difference. So here is a predicted value, what the value actually was in the testing set, and how much they differ. And then I just show that, basically. Again, this was covered in the previous lesson, so feel free to go back and look at that. And here we're just generating that regression summary and producing our error metrics. And now that is just one potential model you could use, that being support vector regressor, but there are many, many, many more models that you can use for regression. There are neural networks, there is linear regression, there are what we're about to go into, regression trees, and random forest regressor, and plenty of others. So never feel a need to limit yourself, but know that which one you use is going to be dependent on what kind of data the model can work with. For instance, what we saw here is that support vector regressor is only able to work with continuous inputs. But the one that we're going to go through now, regression trees and random forest, can work with both categorical and continuous predictors. And you do not need to scale your data. And that makes these a lot more flexible. But the reason why you might choose to use this in place of or in addition to other models is because you never know which one's going to work the best until you try several of them, right? So here I have my regression tree and random forest regressor, and I'm just clarifying what I want to work with here. Basically, I'm saying I want to look at everything except for price, and then predict the price. This is basically just generating binary encodings for our categorical inputs, and splitting the data once again, 80-20 splits. And here I'm doing a simple regression tree, generating the predicted actual results and the residuals, like so. As you can see, the residuals are significantly smaller than they were in the other model, which could suggest this model has performed quite a bit better. And as we look at our regression statistics, we do see that our MAPE did drop significantly, as did our root mean squared error. So it does seem to have performed better than the other model. Now, there's another thing that you may need to do with any model that you work with, and that is parameter adjustment. Parameter adjustment is basically tooling with how the model works in order to get a better outcome. So for instance, here, I have a classification tree, and there are 3 main parameters that we may want to adjust. So here, I'm feeding it a list of the different values that I want to test for the parameter called max depth. And I'm doing the same thing for min sample split and min impurity decrease. And a list of parameters for any model can be found in scikit-learn's documentation online. These are the 3 main ones for classification tree, hence why they're here, but there are other ones in that model, and other models are going to have different parameters. This just gives you a rough idea of how to do parameter adjustments. And now I'm going to import something, again, from scikit-learn called grid search CV. Basically, what this is going to do is look at subsets of your data, in this case 5, and then run every possible model based on the inputs of the parameters that you fed it. So here, it's going to work off of 5 samples of data and do 5 times 5 times 5 different models. And it's going to tell you which one had the best accuracy and your best parameters. So now you can instead feed your decision tree regressor your now tuned parameters. Say here, like this said, max depth is 5. Obviously that has changed since the initial time I ran this, since it's now 10 here. But this could be 5. Min impurity decrease is 0. And min sample split is 50. And now we fed it the exact parameters we want it to use, and we can train the model, store the predictions, and show our error statistics once again. And here, it has not really improved the model at all. In fact, our MAPE increased significantly from the other one. So we can't say that it made it better in this case, but that doesn't mean that you should throw out parameter adjustment in every case, because you never know when it's going to improve what you're doing. Because I've seen cases where it improves model performance drastically. I've seen cases where it's about the same, and as you're seeing here, it can make it worse. But you never know what you're going to see until you try to do it. And now, we talked about the classification tree a little bit, but here we're going to talk about its brother, which is called the random forest regressor. Random forest will basically use a tree-based classifier, like a regression tree, and put it through the bagging process. What bagging basically does is split your data into random samples and run multiple of the same model in tandem, and then combine the outputs of those models into a final output. This, in theory, can improve model performance, hence why we're trying it here. You can do bagging with any model, but Random Forest has one that's specifically implemented in scikit-learn. If you want to do it with another model, you can. You just have to install another package and clarify the model that you want to use in the bagger. Okay. So Random Forest is easier to code, hence why I've used it here. So here I just say, I want to use Random Forest regressor, state it, train it, create the predictions, store them, and the results again, residual, actual, etc. And our MAPE has gone down compared to a simple classification tree. So, seems to be good. Which one is best? You would have to compare all the statistics together. Again, main ones, RMSE, MAPE. If you want more clarification on that, please watch the previous video. Now, we talked about regression, and that being a supervised machine learning model that can predict a continuous outcome. But now we're going to get into classification, which can predict a category, whether that be a binary one, say true, false, this food is like a fruit or it's not a fruit, or multi-class, you can say whether it's fruit, vegetable, or something else. Now we're going to look a little bit into class imbalance before we get into specific models. Basically, what class imbalance means is in your training data, you may have a case where the thing you're trying to predict does not have equal distribution across the possible classes. So here, I'm trying to predict the room type. And we can see that entire home and department makes up about 52% of the market. A private room makes up about 56% of the market. I'm sorry, 46% of the market. And a shared room makes about 2% of the market. And that's a fairly large imbalance, right? This one here is barely getting represented at all. So if you have that imbalance in your training data, your model may not have enough samples of your small class to learn well with. And to resolve this issue, we try two techniques, that being oversampling and undersampling. Oversampling will generate new data for your small classes. So here we have shared room and private room being smaller. So basically, it would generate new data for these classes until it has an equal distribution all the way through. Say 33%, 33%, 33%. Right? It's inventing new data for the model to work with. And you can do that pretty simply. You just define whichever oversampler you want to use, and then you do fit resample to oversample it and specify that you want it to go into your training and your other training. And of course, this code and the data will be provided. It will be on our website, txdata.club, and I can always send it to anybody who requests it. Now, undersampling does pretty much the exact opposite of what undersampling does, or what oversampling does. Do I have a link to the notebook? Okay. What I can do is send it after the fact. The problem is right now I don't have a local version of it, and if I just share the file that's on Google Colab, it will cause issues if somebody else tries to run code. Because it will just be a shared file at that point, and that's going to cause issues. But yes, everything will be on the website, and I can send it directly after the fact, just whatever is easier. Right, and here, undersampling does pretty much the opposite of oversampling, like I was saying. Instead of creating data to match the largest size, say here, generate new data for private and shared room, it will take away data from your large classes until it has the same number of samples as your smallest class. So say, like we have our classes, A at 1,000, B at 2,000, C at 500, it would cut from A and B until they both equal 500. And basically, it's just going to choose those samples at random to delete. And now we're going to get into some different classifications. And there are really two main forms of classification that you can do. One is binary classification, and the other is multi-class classification. How does oversampling generate the new synthetic data? Yes, it'll depend on the oversampler you use. The one that I have here, if I can find it again, is random oversampler, and that will simply look at your data, select random rows within it, and then duplicate them. There's another one that's called SMOTE, SMOTE, and that one will generate truly synthetic data. So it'll have unique values compared to anything else in the dataset. And which one is better? I don't think it matters too much. No problem. Right. Here, I'm looking at a naive Bayes model, which is basically entirely run with probabilities. And there are three main forms of naive Bayes. Those being Bernoulli, where all of the predictors are binary, Gaussian, wherein they can be continuous so long as they are normally distributed, and multinomial, in which case they are continuous, but they are count values. I guess that might make it ordinal. I'd have to look into that, but yeah. Right. Here, because I'm going to be using the Gaussian one, I need to make sure that my data is both continuous and normally distributed. So here, I'm saying, hey, make me a normalized form of X-train using X-train looking at our two continuous predictors, those being service fee and price. And I'm doing the same thing with the validation data and also the oversampled and undersampled forms of the training data. You will never over or undersample your validation data because it's not needed. You only need to do over and undersampling for your training data. Because the only reason why you do it is so that the training process can be more effective. It needs extra samples to learn from underrepresented classes. But you don't need that for predictions, if that makes sense. Right, so I've normalized them into normal distributions. And here I'm just getting Gaussian naive Bayes and predicting a multi-class classification report. And again, you can use any one of these naive Bayes forms. Pretty standard stuff. And you will also want to test to see how well over and under sampling, or you'll want to see if over and under sampling has affected model performance. It might be the case that it learns perfectly well on unbalanced data, especially if you have a very large data set where all of your classes have large sample sizes, but that's often not the case. So it's always good if you have class imbalance to see if oversampling and undersampling makes a difference. So up here, I ran it on normal data, but here I ran it on oversampled, and the next one I ran it on undersampled. In this case, it made no difference, which could suggest one of two things. One, these predictors are not relevant to our outcome at all, or it could just mean that this model in particular is not good at predicting this, in which case you would want to try other models or to try bagging or boosting, which we're going to talk about next. Boosting is similar to bagging, like we talked about earlier in the random forest model, but it works a bit differently. Boosting will feed your data to a model, and then it'll look at all the samples that it did not properly classify or regress if you're doing a regression boosting model, and feed that to another model to try to predict the value again. And it'll basically do that for however many models you specify, with the end goal being that through each iteration, it gets a bit better at predicting these values, so your outcome is a higher accuracy. So again, bagging, basically you have multiple models running in tandem, and then you combine the outputs at the end, and this one is sequential. It'll look at everything, look at the ones that didn't predict well, feed it to another model, and iterate over that process for however many models you have. Right. And as I was saying earlier, you can do bagging and boosting with any model. And here I'm choosing specifically to do boosting with Gaussian naive Bayes, the model that we just used, basically. Here I'm saying, hey, I want to do a boosted version of Gaussian naive Bayes using 10 models. And then I'm going to fit it, create the predictions, and do the classification again. And once we do that, it made no difference. Again, maybe another model will be better, but at this point, I might suspect that this data is just not very well correlated. Right, so that gets you through supervised machine learning pretty well. Again, basically, you have a data set with all your predictors and your outcome that it'll learn from, and it'll use what it's learned to predict your outcome for another data set that doesn't have that outcome already. But unsupervised learning doesn't have that target in the training. It'll just have, say, your predictors or whatever, and it'll try to learn from that and do something. How could it do that? Because it's not really trying to predict an outcome that we know. It's trying to do something a bit different. And here's some ways that it does that. First are association rules. Association rules will basically look at the variables that you have and see how correlated they are to one another, but in a more complex manner than a simple correlation matrix. So you can see, hey, given that this thing happens, this other thing happens, but you can also see, given that, say, A, B, C, and D happen, that's the probability that F will happen. And this can be good for text mining and for other situations where you have a lot of predictors to sift through. Because you can imagine that if you have a large text data set, you're going to have many, many, many thousands of words to consider, and not all of them are going to be relevant. Association rules can show you how correlated things are and tell you, okay, if all of these words, or if this word is really correlated with this one, we can probably get rid of these other ones and not lose much information. And in doing so, you can improve your model runtime and potentially your performance as well. But that's just one example of how you could use association rules, and it's what I'm most familiar with. But again, it doesn't have an outcome to learn how to predict. It just looks at relationships within your data and tells you something that you don't already know about it. Clustering does a similar thing in a way. It basically identifies categories that you aren't aware exist in your data. So clustering can look at all of your predictors, say that you're a marketer and you have data on all the people that have bought products with your company, but you don't really know who your segments are because maybe they're too diverse or your company is new, you just got into it, or something along those lines. You basically don't know what you're actually looking at. If you can take that customer data and put it through a clustering model, it might be able to identify market segments within your data. Again, it will look at relationships between your data, see how things co-occur and stuff like that. And you can define, hey, I want you to find 3 clusters, 5 clusters, 7 clusters within this data, and it will do that. How well it does that is up for human interpretation. Usually, it'll show you which features are most important to the clusters. And by looking at those features, you can identify how relevant the clusters are and choose how many you might want to use, right? But you can imagine these things are basically running off of machines and they don't really, they're not subject matter experts. They're basically just trying to look at the mathematics behind everything and see how things occur together and create something. And that might not always be accurate, which is why we're still around to try and verify what they're doing, right? Sentiment analysis is another form of unsupervised learning, and it's pretty specific to text mining. Basically, sentiment analysis will look at a given text and determine how positive or negative the sentiment it expresses is. So say you feed it a bunch of social media posts, and it'll look at each post and say, hey, this has a sentiment score of X. If that sentiment score is higher, that means it's more positive, and if it's lower, it's more negative. And you can establish thresholds if you like to determine positive and negative, exactly where you want that line to be, but that's not truly necessary given that this has a numeric outcome. Now, machine learning can also be used with image and video data, and what exactly you might want to use with that data, or do with that data rather, can get pretty specific and different from what we've talked about here, but we're not trying to cover that in this. We're mostly looking at pretty standard data science tasks, especially within the business world, because you're usually not looking at image and video data with that. In most cases, you might end up doing it if you're somewhere at a social media company or something like that. Now, statistical modeling is the most similar to supervised machine learning in that it can learn how to predict an outcome and predict outcomes. So it's very similar in that regard. The main difference between them is that statistical modeling will be able to show you the relationships between your variables much more clearly than a machine learning model will be able to. So why don't we use statistical modeling? Machine learning is usually used more often than statistical modeling in business situations because usually in those situations, we don't need to know the relationships, but also the accuracy provided by machine learning models is typically higher than that of statistical models. However, statistical models can be applied if you need to know the relationship very well, especially if you're working in a research capacity. You can imagine that a physicist probably wants to understand what is happening more than a business person that's just trying to figure out, like, I don't know, will the line go up, right? And also, machine learning models are typically better at working with large data sets, which again lends itself well to the business world. So I'm going to show you some pretty basic versions of this, those being through the stats models package in Python. And again, it has documentation online, so feel free to look at the different models offered within it and some of the other tools that it provides, because it also has some basic statistical tools in it as well that go beyond these models. So here we're going to look at a regression model. I'm feeding it my data, getting dummy variables, and saying, hey, this is going to be my x, this is going to be my y. And now I'm going to fit it through a linear regression statistical model. Basically, I'm saying, hey, I want you to predict y based on these outcomes which have been defined in variable x. And now I'm printing my summary results. You can see this is much more verbose than what you saw earlier. So this tells you more information. Basically, R squared can be used in place of accuracy. You can look at your coefficients, your p-values, and everything, and that will tell you which ones are the most relevant to your outcome, right? And I go into more depth about this in the previous video. Once again, gonna keep liking that one because it is very relevant. And all of our videos can be found on our website, which will basically link to our YouTube channel. Again, that website is txstatedata.club. But yes, I see small r squared hasn't done that good of a job. And there are some low p-values indicating that those might be more relevant variables. So you might do some feature selection at this point and say, okay, I want to use only the most relevant predictors. So feed those to the model and see if it improves anything. And from there, you can go and use a machine learning model if you wish to. Now, classification, you can do that as well, but your outcome is going to be a little bit different. Instead, you're basically going to get something called the pseudo R squared, which again will look at basically how accurate your model is. And you'll also get your p-values, which are still relevant here, basically read the same way. Here, pretty much nothing seems to be that relevant except maybe calculated host listings counts. And we can't infer anything from the pseudo R squared because it's decided it's infinite, right? We can't really gauge what that means. But in this case, we did a binary classification using logit, but we can also do a multi-class classification using logit. And both of these are from the stats models package. So here I'm trying the same thing, but now I'm trying to predict every room type instead of just whether or not something is a home or apartment. So here I'm seeing results for private room, shared room, and the final one simply isn't showing up, presumably because it didn't classify anything into that particular class. And we can see that our pseudo R squared is very low once again, so it hasn't done a good job. And we can look at our p-values again. We see that it's relevant for private room, but not relevant for the shared room, which is interesting. That could lead us to believe that it's really not that relevant at all, that we can't predict anything, or we can try filtering down to just that and see if it has had an effect. And you can use these statistical models, again, to improve your machine learning models or use them on their own. Because model performance is partially dictated by the features that you use. In this case, we're seeing that some are more relevant than others, so we can select the ones that are actually relevant and feed that to our models to make things perform better. And that is something called feature selection, and that's a subset of something called feature engineering. Feature engineering is pretty much just a broad term saying, hey, here's how I want to prepare the predictors that we're using for our model to work with. So we worked with converting things to a Gaussian distribution. That's one way you could do feature engineering. We scaled our data. That's another way you could do it. We, at points, got rid of categorical inputs because they wouldn't work with our model. That's yet another form of feature engineering. And we can use these statistical models to show us which ones we should select. And once again, that is feature engineering. It gets more broad than that, but that's the basics. Basically, you want to make sure that your variables are suited for the model that you have and that you have relevant features. And an important thing to note about any model that you're running is that they are somewhat dependent on the size of your data as well. So if you recall at the very beginning of this, I reduced our sample size down to 1,000. Normally, this data has, I believe, about 500,000 rows of data. I would have to look at it to verify that, but I'm going to go with that number for now. And we use support vector regressor. Support vector regressor and support vector classifier, which are both subsets of support vector machines, being the main model, are good at working with small data sets, and they usually have high accuracies and can classify things well. But if you have exceptionally large data sets, the runtime can increase to something that is not manageable. So for instance, whenever I was trying to run this with all of the data, all 500,000 rows or so, it was taking entirely too long for the code to run. Hence why I chose to reduce it down to 1,000. There are other models which are exceptionally well suited to large data. And some of those are your random forest models and neural networks. Neural networks work a bit differently than other ones, but this is mostly an overview, right? So that's pretty much what I have right now for this particular class. So I'm happy to answer any questions that y'all have regarding any of the models that we've used, other models, neural networks, anything along those lines, right? So ask away.
Questions as such, but this was really informative, Max. Thanks a lot.
Yeah, no problem. No problem. Right, I see something in here. Are you using Google Colab free tier? Yes, this is entirely free. Yep. And for those that may be unfamiliar with Google Colab, it's basically Google's Python environment. Specifically, it's a Jupyter notebook. And you can use pretty much any data that you want inside of it by either putting it in your Google Drive to connect to directly or uploading it into the file runtime for the notebook. Now, if you're working with very sensitive data, then I wouldn't recommend using Colab for it. But if you have, say, a large data set that you really don't care if Google gets their hands on, Colab is good for that. because Colab will help take away some of the processing from your computer to Google systems, which will allow you to work with significantly more complex models and larger data sets than you may be able to on a laptop like I'm working on right now. But again, if you're worried about the security of your data, I would not recommend using Colab for that. Various GPUs, yep, they have that. Right. Yeah, no problem, Lucas. And do remember that we do have a competition going on right now. And I sent the data in a previous email, and I can send that again if anybody needs it. But that is going to be due in 2 weeks' time. You can work in groups if you wish to, but the end prize of that is going to be $25 for each person that is in the group. So if it's a group of one, you'll get $25. If it's a group of three, then it's $25 per person. Basically, it'll work like that. And I'll be announcing that more formally in the upcoming hours. Right. Now that we have our machine learning class out there, people can refer to that, and that'll make the project a lot easier, I think. But yeah, that's ongoing. It's with housing data. Once again, basically it's easy to work with, and there are a lot of variables involved, so you can pick and choose whatever you want to work with, right? But yeah, any more questions before we sign off? Yeah, so I announced the details of it in a previous meeting, but I am going to be sending the details to everybody directly because I know that not everybody was able to make it to that. But basically, we have a data set that's looking at housing primarily, and it has a bunch of different factors like, say, foundation, square footage, the year was built, the year was remodeled, etc., price, and you get to choose whatever thing you want to analyze and however you want to analyze it. And it'll be running for the next 2 weeks from today, 2 weeks. And at the end of that, you'll basically be submitting a report of everything that you found along with your code for us officers to look at and basically determine a winner from there. Again, if you want to work in a group, you can. If you want to work on your own, you can. And we're going to say groups that are no larger than 4. And every person in the group, regardless of its size, will win $25 if they win the entire competition. I think that pretty well covers it, but if there's any more questions about it. All right, cool. Right. Well, it seems like we're pretty much done, so I'm going to stop the recording soon.